Okay, in this next problem, we are finding the electric field at point P, a distance x away from, put x in here, a distance x away from the center of a charged ring, a uniformly distributed positive charge Q spread along that ring. Okay, so like before, we have a charge distribution. So if we look at the equation for an electric field due to a point charge as kq over r squared r hat. Okay, so this is due to a point charge. We can't use that here because we have a distribution. But we can look at little pieces of the distribution and dq, and notice the dE1 corresponds to dQ1. So we take this tiny portion of the charged ring, which has some charge element Q1. That's going to create a field over here at point P that equals dE1. Now, since this is a positive charge, the field points away from it. Same thing over here. dQ2 is going to create dE2. What you may notice, though, is that the y components here cancel out because, well, let's draw it. dE2 is composed of dE2x and dE2y. However, the other electric field on directly the other side, dE1, is also going to have an x component. I'm sorry, it's getting sloppy. dE1x, and it's going to have a y component, dE1y. You notice the y components cancel out, and this is going to be the same thing all around the circle. Since all of these y components cancel out, I've shown that, then I can write dE as kq over r squared cosine of theta I hat plus 0 j hat. Because this x component, if this is theta, the x component is going to be cosine of theta. It's going to involve cosine of theta. So what is r? This is where things get really confusing because I've made this capital R over here and set that equal to a. That is the radius of this circular charged ring. There are lots of radii going around and everything, but remember this r is simply the distance between the electric field measured at some point and the charge creating that electric field. So it's the distance between point P and dQ1, for example. And of course we know this leg of that triangle is equal to x, this leg is equal to a, so therefore r is equal to square root of a squared plus x squared. So I can actually write that in and insert that into the equation. So dE is equal to kq over, and when you square this, the square root goes away, a squared plus x squared times cosine of theta. Label that, and that is in the I hat direction. Now, I can actually make one more simplification. Cosine of theta, well, let's get that in like terms to everything else here. Cosine of theta is equal to adjacent x over hypotenuse square root of a squared plus x squared. So I can insert that into the equation. dx equals kqx. Now this is going to be to the 1/2 power times the first power, so I can combine those two, a squared plus x squared to the 3/2 power. Oh gosh, I forgot the dq everywhere because this is a differential charge element that creates a differential electric field. Sorry. Okay, so what you notice right now is that none of these things, the charge does not depend on any of these things. Like in some of the other equations, if you remember, dq was equal to, like one of the very first problems like this that we solved, lambda ds, which is equal to lambda r d theta, because remember you had that arc of charge and you're looking at dq, and so the charge element, the magnitude of the charge element dq depended on the angle that you swept out when creating that charge element. So dq depended directly upon d theta. In this case, it's not that situation. dq doesn't depend on any of these things, on x, on a, on k, none of these things. So I can take everything out of the integral, kx over a squared plus x squared 3 halves, and that just leaves me with dq. Well, if you integrate that, once you perform the integration, the electric field then equals kxq, which is the total charge of the ring that we're given in the very beginning of the problem, over a squared plus x squared to the 3 halves. And that's your answer.